Okay, so this is section 8.6, representations of functions as power series. So we've learned about power series in section 8.5. What we're now going to talk about is how we can use power series to learn more about functions. So we can actually represent power series with functions and functions as power series and back and forth. And that gives us a lot of ability to do some very interesting things. So we start off with this particular power series, which is just the sum of x to the n power. And from our knowledge of geometric series, this is like the sum from n equals 0 to infinity of, that wasn't supposed to happen, 1 times x to the n. That 1 is our a, that's going to be our first term. And our x is our ratio. So this is going to converge to a over 1 minus r. That's what geometric series converge to. But in this case, that's 1 over 1 minus x. But only in the situation when our ratio, x, with the absolute value of that, is less than 1, right? That's our rule for geometric series. So in other words, this thing, if I wrote f of x equals 1 over 1 minus x, that is a function. And we can, in fact, represent that function, 1 over 1 minus x, as this power series, which is really just a polynomial that goes on forever. And it only works, though, for certain values of x, or the values between -1 and 1. And another way of thinking about this is that the partial sums of the power series give you an approximation for the function. The larger the partial sum, the better the approximation. So I'm going to try to do this. I'm going to jump back and forth between this picture here and Desmos. So the first thing is if I graph 1 over 1 minus x, that has a vertical asymptote here at +1, because that's when we'd be getting 1 divided by 0. So that's at 1. And the graph of this, maybe I'll graph it in red. As x goes to -infinity, this becomes 1 over infinity. It goes to 0. And then as we get closer and closer to +1, we're going to be getting a really small number down here in our denominator. And we'll be getting 1 divided by a large number. It's going to go to infinity. And yeah, when x equals 0, it crosses here at 1. So it's going to look like this. And hopefully this is going to work. I want to pull this up in Desmos. There we go. That's that same red graph that we had before. The difference being mine is a little bit uglier. And the idea is we know that this red graph there, that's 1 over 1 minus x, it's equal to this power series we talked about up here. And so if I start adding up these terms, suppose I look at, just the first two. Suppose it was just 1 plus x. So if I just chopped it off and I only looked at the first two terms of that power series, that's going to be close to my function, but not exactly. And let's see what Desmos tells us. Where is that? Here we go. So if I click on 1 plus x, that's the black line there. So it's going to be 1 plus x is just a straight line. It intersects my curve at the y equals 1 spot, the y-intercept, but it doesn't really intersect anywhere else. So let me graph that here on my picture. So that black one, it's basically going to look like that. And my Desmos graph is zoomed in to be just between -1 and 1. And what I want to do now is I'm going to show you on the Desmos picture. Maybe I should use a different color for this. But I'm now going to just start adding more of these terms. So I'm going to add in x squared, and I'm going to add in x cubed, and I'm going to add in, let's do a nice orange color, x to the fourth, and we're going to see what happens to this curve as I keep adding in those terms. So our red is the thing we want to match to. The black is close to that. When I add an x squared, it's now getting curvy because it's like a parabola, and that green curve is a little bit closer to the red curve. And it is curvy, better than the black, but still not perfect. The next one is, whoa, take that away. The purple, let's see if I can compare that to the green too. You can see the purple gets even closer to the red, but it's still not quite on it. And then I'm going to do one more. The blue, that's to the fourth power, it gets even closer to the red, but again, isn't quite perfect. And really, anywhere you look, like if I was going to look way out here, you know, to one extreme or the other, my blue is always closer to the red in this entire region than any of the other curves. So what does this look like on the picture you're making? I said the x squared, that was with the green. That one sort of looked like this. The x cubed, that was purple. And that one was a little better. It ends up going down at some point. And then the last one we had was the orange. And that one does an even better job of matching the red, but eventually it does shoot back up or something like that. So the point being here is that the more and more terms that you're adding in there, in the same way that you add more terms to a series, you get closer and closer to the sum. As you add more and more terms into your power series, you're getting closer and closer to that particular function that you are approximating. And that's one of the big ideas that we're going to do here. So number two, writing a function as a power series. If I wanted to write a function as a power series, we need to really make the function look like something, a power series that we already know. And right now, the only power series that we know is that one I just gave you, that 1 over 1 minus x is equal to the sum of x to the n. So when I look at this, I think, 1 over 1 plus x cubed. Well, I could rewrite that as a 1 minus a negative x cubed. And this right here is then taking the place of the x that I'm putting in over here. So this thing right here, that negative x cubed, that's like my x. So I'm going to get this exact same expression over here, except instead of an x here, I'm going to get a negative x cubed to the n. And that's from n equals 0 to infinity. And I can rewrite this. This is like, if I take that negative and make it into a negative 1, so it's like a negative 1 times x cubed all to the n power. So that's like a negative 1 to the n times x to the 3n. The nice thing about getting that negative 1 out is then it makes it look more like an alternating series. And if I started writing out the terms of this, it would be like a 1 minus x cubed plus x to the 6th minus x to the 9th plus ... And notice that this thing here, that x cubed took the place of my x. This is only valid when that x was absolute value that was less than 1. So this is only valid when my negative x cubed, the absolute value of that, is less than 1. But of course, that's the same thing as just the absolute value of x cubed. And when you take the cube root of both sides, you just get absolute value of x is less than 1 anyways. So when absolute value of x is less than 1, it will converge. And in this case, that means that the power series will be a good representation. So if I graphed in this, let me phrase that a couple different ways. If I graph 1 over 1 plus x cubed, the same way I did on Desmos before, and then I started graphing 1 minus x cubed, 1 minus x cubed plus x to the 6, 1 minus x cubed plus x to the 6 minus x to the ninth. Each of those graphs, as I add in more and more terms, will get closer and closer to the original graph. And for values outside of -1 to 1, like if I wanted to plug in x equals 14, this representation would not work very well. But if I wanted to get a value for, say, x equals 1/2, well, plugging it into 1 over 1 plus x cubed would give me the exact same thing as if I plugged in 1/2 for each of these x values here in my power series representation. Obviously, I'd have to go to infinity plugging in those 1/2s and raising them to whatever power, but it would work, and I could get an approximation earlier than that. And we're going to see examples of that later.